Good evening, everyone. So, this is your mentor Rahul Ghosh. Again, we are going to start with the next session of alkyl halides and aryl halides. And today, we'll be focusing on the rest of the reactions, rest of the preparations of alkyl halides. We have already covered with your alcohol. We have already covered with preparation of alkyl. I mean, the first part, that is here with alcohols. So we'll be moving on into the next segment, right? Now in totality we have we are going to study 4 different types of preparations. First, we have already covered the one that is with the help of alcohols. So today we'll be focusing on the one that can be done with the help of hydrocarbons, right? Hydrocarbons, say we can make them. It contains both alkanes and alkenes, right? Alkanes bhi hoga and alkenes bhi hoga. Markovnikov, anti-Markovnikov reactions, which you have already done in class 11th, right? Then we have got halogen exchange reactions. Where we are going to focus on fluorine and iodine preparation, name reactions bhi hai. And there is also a very nice reaction called Borodin-Hunsdiecker reaction. Borodin-Hunsdiecker reaction. So we'll explore all of them one by one, right? Let's start. So these are the 4 things that we'll be covering in today's session. Alcohols we have already completed. So right now we are going to focus on preparation with the help of hydrocarbons, both alkanes and alkenes, right? Acha. So we are going to start with the help of your alkanes preparation, in which we'll be focusing on free radical substitution. Right? For substitution reaction, if you remember, we discussed that there are 3 particles, that is you have got carbocations. I mean, for substitution, sorry, you have got nucleophiles, you have got electrophiles, and you also have got free radicals. So here we are going to focus on free radicals. What are free radicals? Free radicals are your atoms. If we focus on carbon atoms, then they have got 1 electron less. It's an odd electron species, right? Like methyl free radical CH3 with 1 electron. Now it is a neutral species. It is neither positive nor negative. Why? Because this electron is from carbon only. Fine. And it is also sp3 hybridized. So this is very useful intermediate which can initiate lots of reactions. Today we will be looking at its one of the features where it can help us form alkyl halides with their help, right? Acha. Now one example that we can see here is that when butane is treated with chlorine in ultraviolet light or in heat, you can see that you have got this as primary position, this as secondary position, again repeat, secondary and primary. So you have got basically 2 unique positions and other 2 are repeats. So technically we should get 2 isomers, right? So you have got 1 chlorobutane and you have got 2 chlorobutane, right? Acha. Now the problem is, here we have spoken only about monohalogenation. Only 1 hydrogen has been substituted. But the problem is that it does not stop here. It goes on adding more halogens, like in this case more chlorines will be added till the time all hydrogens are substituted by chlorine atoms, right? So what happens that at the end you get a mixture of various isomers. So in place of getting 1 or 2 pure compounds, you get a full mixture of various possibilities, which is not as useful as we would like them to be, right? So for example, here you have got how many you have got 10 different hydrogens, right? So all of them will be replaced one by one, and if you get like 10 different isomers, or even more than that, because there can be various chain isomers, position isomers, right? Those kind of permutations and combinations will be there. So you'll end up getting lot more things, and to segregate them into individual pure compounds is going to be a very painful task. So industrially it is not that helpful, right? So still we are going to study about monohalogenation, and if we can take, and that is where, you know, the creativity comes in. Right now you have got options of more than one position, two different isomers, but somehow if we can, for monohalogenation only, if we take those substrates where you can have, you know, only one possible monohalogenation isomer, one possible exclusively, then that is still quite helpful, right? Okay, so what are the various steps, or what are the various steps in mechanism of free radical substitution? So this is something that you have studied in hydrocarbons in class 11th also. So you always first initiate the reaction by formation of free radicals, so this will always initiate the reaction, right? For example, if I am starting with chlorine, or if I am starting with bromine, so in general if I am starting with halogen, so I'll be getting this as the starting product to initiate the reactions. Now this will attack the substrate, right? And this will keep on happening. So hence propagation, the chain is going further in a particular direction. So various possibilities are there. Once hydrogen will be extracted, once halogen will be extracted, and this will keep on repeating in a loop, and the whole reaction will keep on going forward. That is where you come in for the second step, that is your propagation. So here you get actually two radicals, here you get one radical, and in the last stage, till there is even a single radical, there is a possibility of propagation. So if you somehow you know, combine all these radicals into one new molecule, then the reaction can be stopped. So to stop the reaction, to terminate the reaction, you need these free radicals to combine with each other, so that nothing, no single new free radicals is left behind. So that is what we do in termination process. So you can see that here two radicals are combining, so zero free radical will be left behind. So in the first step 2 is formed, in the second step 1 is formed, and in the third step 0 free radicals are left behind. Let's see step by step how it is taken care of, right? So we are going to use the simplistic reaction, that is methane with chlorine. So we will be studying its steps and understand how these three steps take place, same as you did in your class 11th also, right? So what is my step 1? So as we discussed in step 1, that is your initiation, your two free radicals are formed right here. So what is happening, your halogen atom, it is absorbing energy in the form of heat or ultraviolet light. So the bond is going to snap open, right? So homolytic division will take place, homolytic cleavage will take place, and see, that's why we have drawn half arrows over here. So both the chlorine atoms take away their own single electrons, and they end up being chlorine atom, or simply two chlorine free radicals is what we obtain. So the general reaction is you have got X, right? It can be chlorine, it can be bromine, and then you have got this coming over here and this coming over here. So you have got 2x dot. In a simplistic manner we can remember that, right? I'll just check for any doubts from you people. Please feel free to ask if you have got any doubts. Hello, Lakshmi. Hello, Tara Swami. Uh, hello, Srivatsan, Shivranjani. Welcome, guys. So please feel free to ask any doubts that you have got. Right? Hello, Ramya. Fine. Okay. So once this step 1 is initiated, then this free radical is definitely going to attack. We have got methane, remember? So it is going to attack methane, and in the next step it extracts one hydrogen from the methane. So that is how propagation starts. Means initially you have got only 2 chlorine free radicals, and now new free radicals will be formed. So that is your step 2. So you can see that this chlorine atom is extracting one hydrogen atom from methane, and now you have got HCl is formed, but in addition to that you have got this methyl free radical. So a new free radical is formed. So this is one of the possible steps of your propagation. So now what is going to happen? Now it is a kind of a dominoes effect, right? So this methyl free radical, either it can attack another Cl2, or it can attack HCl also. It is going to extract one of the Cl in the next step, and then again Cl free radical is formed. It is going to extract one more hydrogen atom. This is how slowly, one by one, all the hydrogens will be extracted and chlorine atoms will be replaced over there, right? So you can see in the next step what we have, this methyl free radical, it is extracting one of the chlorine atoms, CH3Cl is formed, and again you have got a new chlorine free radical which can again propagate further by extracting another hydrogen atom, maybe from this molecule or like this from any other molecule, right? It's a random process. They are simply colliding and extracting atoms from one another, right? So ultimately we come to chain terminating step. Like in propagation process, it is not necessary that every time the same free radical is formed, new free radicals are formed, right? Similarly in terminating process also, these are all various possibilities. So the main thing that we have to keep in mind is that one free radical is going to combine with another free radical, and they will stop forming any new free radicals. Got it? So now like this, methyl free radical may combine with chlorine atom or chlorine free radical. 2 methyl free radicals may combine with each other forming ethane, right? And similarly 2 chlorine atoms may combine with each other and forming the chlorine molecule again. These are all various possibilities. There could be more possibilities because there are other free radicals also in the system which are being formed. That is how we get the third termination step, right? Any doubt, please feel free to ask, bachon. Okay, now as we discussed a few minutes back, there are possibilities of alkane. There are few alkanes where you can actually have only one single monochlorination product, right? So methane is one of them. Monohalogenation can be done at only one particular position. No other variations are possible. So of course we are dealing only in monohalogenation. We know that further di, tri, tetra, polyhalogenation can take place, but we are focusing only replacing one hydrogen atom. How do we go about it? You have, for methane we understand, even for ethane, all the hydrogens, all the 6 hydrogens are equivalent, and hence you replace any one of them, it's all the same. Then you have got 2,2-dimethyl propane, right? You can see. So all of them are exactly similar position. All these 3 hydrogens are exactly equal to other 9 hydrogens. That means you have got 12 equivalent hydrogens. So you replace any of them to start with, it's one and the same, right? Now in case of your toluene. It's a very interesting case. In case of toluene, this substitution is not going to take place on the 5 hydrogens present on the aromatic benzene. These are not going to undergo such replacement very easily under room conditions. So you have got these benzylic hydrogens, right? And these benzylic hydrogens can be easily replaced. All 3 of them are equivalent. In fact, it's if you see the order, benzylic hydrogen atoms are most reactive here. Proof is, if you have, say, ethyl benzene, right, and you react this in sunlight, say with chlorine, so what you are going to have? You are going to have majority of, as a monohalogenation product, majority of it as this. Chlorine will come over here, right, this position. So this is your benzylic position where chlorine is going to come, and the of course the mechanism is going to be your free radical mechanism, right? Why this position? Because this free radical, very important to understand this, this free radical is, benzylic free radical is resonance stabilized, and more the number of resonating structures, more the stability. You must have studied in GOC in class 11th. Right? So I hope this part is absolutely clear to all of you, why these compounds can be used for monohalogenation, because every hydrogen behaves in a similar fashion here, right? Okay. Now, when we talk about alkenes, next segment after alkanes, when we talk about, okay, still in alkanes, I thought we are in alkenes now. In alkanes, there is something called allyl substitution. In alkanes, we have got something called allyl substitution, which is again very important, especially for conversion reactions, even for your those step up and step down reactions also, we can employ the allyl substitution beautifully, right? So basically what happens, we just talked about resonance stabilization. The similar thing happens here also. You can see, if you use propene and similar conditions of ultraviolet light or heat, exclusively you are getting allyl chloride. That means the allylic position is exclusively employed. Why? Because once in the mechanism, you will see that once this hydrogen is extracted, you have got the free radical over here, which can show you again a resonating form. Like this will come over here, this can come here, and it can move over there. So what do we have? We have it, the other structure as this. So you can see that here you have got 2 resonating structures, and hence stability of this allyl free radical is quite good. So you always get allylic position occupied by the incoming halogen, right? Same you can see here also. In case of butene, we are getting the same stuff, that is the allylic position is getting occupied by Cl2, right? Okay, one possibility is here, because resonance is taking place, this is formed. Now this is where you have to think little intuitively. See, as I told you, in the case of propene, whether you take this or this, it's one and the same thing. But in case of butene, there is a twist. The free radical that is formed initially is this, but when it will undergo resonance, it will come here, right, and this will go over here. So the resonance part that you get from here is this, the other canonical form. And you can see that this was coming, this is initially, this was primary free radical, this is primary free radical, this is secondary free radical, primary free radical, while this is secondary free radical, right? So here you have got another isomer, which is this, and secondary is always more stable than primary, right? I hope this part is very much clear to all of you, right? Fine. So no doubts, I'll proceed further. Okay, as we discussed in case of benzylic, I just discussed it few moments back. Benzylic is always more stable than any other type of free radicals because of its resonance, right? Aromatic resonance here. So hence, whenever you react any such type of compound with your bromine or chlorine for that matter, you'll always get it over here, that is at the benzylic part exclusively, right? I'll give you one question, you guys try to solve it, and we may discuss this towards the end of the lesson. Right, I'll give you chlorine and ultraviolet light. I need only the major product here, I need only the major product out here, right? And you can think about it, you can copy it down and let me know what is the answer towards the end of the session, right? Okay, I'll move further. I've given this you as classwork only, think about it in between the class. Okay, now another method of getting allylic substitution, free radical substitution, is by use of this very famous compound, famous reagent called NBS, right? N-bromosuccinamide, right? So you have got succinamide over here, and when you react this with HBr in with bromine in presence of CCl4, that is when you get N-bromosuccinamide, NBS, right? This is very important reagent industrially also and very useful. It gives your free radicals bromine, I mean without using your heat or ultraviolet light also, you can exclusively use this, right? The best part is it gives us bromine free radicals as and when needed, and also the concentration of bromine maintained is always very low, very low. So it helps in creating an environment where we can have this product, bromine substituted product, in a quite good manner. I mean the yield is very good here, right? Okay, so we had been talking about substitutions mainly by chlorine or bromine, free radical substitution mainly by chlorine or bromine. The output is always same, that in case of your free radical substitution, it is always benzylic followed by allylic. Quite similar they are, still marginally benzylic should be more than allylic. Then you have got tertiary, secondary and primary, the same order as followed by carbocations also, right? Now the thing is, you have got these things over here. If you focus only on this part, we have obviously tertiary more than secondary more than primary, so that goes for both bromine and chlorine, it goes for both of them. But you can see that when you are using chlorine, right, okay, secondary is still major, it is still major, but you see it is 45% and it is 55%. However, if you go for bromine, the same figure now looks very weird, right? You can see that this is still secondary is more than primary, but secondary is very large, right? The amount of product in secondary is huge, right? You can see that 3 is to 97 here and 45 is to 55. So it is not much of a difference in case of chlorine, but it's a huge difference in case of bromine. So basically what is happening? Here is the rate at which the carbon hydrogen bond is broken by chlorine or bromine. Now bromine being bigger is quite sluggish in nature, so it is not able to break the CH bond as quickly as possible, and hence it chooses to be more selective. It does not want to waste its own energy on any hydrogen that it is going to encounter, so it is definitely going to follow this order more efficiently than chlorine. Now chlorine is very fast, it has got a lot of energies, so it can break primary, secondary, tertiary, whatever comes in to its come in its path. So in its zeal, in its enthusiasm, it ends up having a lot of primary also, because it encounters a lot of them. Bromine has got limited amount of energy, so it utilizes it well and only goes for the preferred product. So despite getting secondary, in this particular example, despite getting the secondary substitution as major, in case of bromine it is huge, the difference is huge, while in case of chlorine the difference is not that large. So remember these two statements: chlorine being more reactive is less selective, yet bromine being less reactive is more selective. And throughout the your organic chemistry, this is the case. Bromine will be always more selective, even in other reactions that we'll discuss in due course, right? Okay, welcome Shivani and everyone. Still, if you have got any doubts, please feel free to ask me, right? So we'll move further. So we have discussed this selectivity by halogen radical breakage, how the energy factor plays its role. Okay, let's do a question now. Similar question we did last time also. What we have got here? Among the isomeric alkanes of molecular formula C5H12, right? So you have to identify those isomers which are going to satisfy these conditions, right? Now when you say C5H12, think about the isomers that you can have with the help of this, right? And the isomers that you can think about is, one is a straight chain one, N-pentane. Then you also can have 2-methyl butane, and third you can also have 2,2-dimethyl propane. So let's check all of them one by one. So if you have monohalogens, you can have, from the first one, that is from N-pentane, you can have 1 halopentane, a new one is going to be 2 halopentane, 3 halopentane, but then it is going to be repeat, right? So this will be again 2 halopentane and 1 halopentane. So that means from this N-pentane isomer, you can have only, suppose if we number it or say A, these three structures are A, B and C, right? So from the first structure, you can get 3 different monohalo isomers, and the option is 2. You see, 3 isomeric. So that means here you should get the structure A, right? I hope this part is clear. Now you have got in B 4 unique positions, right? This one, third and fourth. This is a repeat of this, right? It is pure repeat of this. So therefore in structure B you can have 4 single monochloro isomers, and the option is third, it is asking for 4 monoisomeric isomers, so it should be B, right? And obviously then one should go for C. You can see that this position has got no hydrogen, it's a tetravalent one, it's quaternary position. So rest all the hydrogens are equivalent. Rest all the hydrogens are equivalent. That means this one is as good as other 3. So only one possibility of replacement, and hence as we discussed, this should be C. I hope this concept is clear, right? Okay, next one. So I'll give you all 30 seconds to think about it. Very easy question. Should not take more than 30 seconds to think about. Okay, so if you have worked it out in your copy, so let's see. It says you have got a hydrocarbon which has got formula C5H10. It seems like an alkene like formula, right? Does not react with chlorine in dark, okay, but gives a single monochloro compound in bright sunlight. But if you draw any alkene, then the thing is that it is going to give you more than one possibility of various monochloroisomers, more than one possibility of monochloroisomers. So if that is the case, then it is going to be difficult to predict which one it is going to be. Now it says that it has got only single monochloro compound. So why alkene? Even cycloalkanes are kind of like functional isomers of alkenes. They have got the same formula, CnH2n. So if you think in that fashion, the only thing that should come to your mind is cyclopentane. Now all the 5 carbons and their respective hydrogens are equivalent. So you replace at any one particular position, it is as good as any other 4 position. So this is your output, right? Only one output, nothing else can be formed, right? Okay. Now it's a interesting part. You have covered it in class 11th also, right? So what we have here, so whenever, see, we have done already the substitution reactions, free radical substitution we have covered, right? From alcohol also we have covered the substitution part. We did it in terms of your nucleophilic substitution reaction, SN reaction. So now after substitution we have got the addition reactions. So adding across a double bond and forming 2 new sigma bonds is nothing but an addition reaction, right? So here you can see very well that if you have been given an alkene, so this hydrohalide HX is going to add across it and giving you HX. Now if you had written it like this also, it's still the same thing. I mean, you cannot make any difference. So if it is symmetric in nature, then whether you obtain this product or this product, both of them will look alike. You cannot make any difference, right? Acha. And what are we going to add? We can add like HCl, we can add HBr, we can add HI, and the order of addition is always HI more reactive than HCl faster than, sorry, it should be HBr, right? HBr more reactive than HCl. HCl. It should be something like this. Now, but if it is unsymmetric alkene, in that case you will be able to decipher that whether the halogen part has gone towards left or towards right, because two different isomers will be formed, and of course one will be major and the other one will be minor. The major one is always obtained as per the Markovnikov addition rule, right? So basically asymmetrical alkenes, whenever you deal in asymmetric alkenes, we always get a product which is predominated as per Markovnikov's rule. This is very important for us to understand, right? Acha. So again, with propene we can have this example. You can see I could have been here, I could have been here, but if I comes at the center, then that is as per the Markovnikov addition rule, and therefore that is always the major. This is the major part. For the major part, you can also remember this statement which you might have studied in class 11th also, that is rich gets richer. Remember this, rich gets richer. So basically what is happening here, if you see both the positions, this position has got one hydrogen, this position has got two hydrogen. So out of these two, this position is richer, right? So in the major product you can see that it initially had two hydrogens and now it has got three hydrogens. So rich simply got richer. Out of these two positions, this one is richer. So a rich position became further rich, it became richer, right? So that is how you can remember what is going to be your Markovnikov addition product, right? So let's study its mechanism. Its mechanism takes place by the help of carbocation formation, right? Initially what happens, Hi being a very strong acid in this particular example, Hi being a very strong acid, it is going to get dissociated as H plus and I minus. Now H plus being small, it is going to travel fast and attack the propene molecule, and you are going to have two different addition products. One is this and the other one is this. Hydrogen, if comes on the secondary position, positive charge will be here. So you can see that you have got secondary carbocation and you have got primary carbocation. We all know that the order is tertiary, secondary, primary. So in this case, secondary carbocation is going to predominate, and hence when now I negative follows, so you get this, and from here you get this. So this automatically, since secondary is more stable, so higher percentage of secondary carbocation is formed, automatically this becomes your major and this remains as minor. The same thing that has been explained over here. You can see that this is minor and this is major. So that is the mechanism behind it, right? So next we talk about same thing, but this is in presence of peroxides. This whole thing is in presence of peroxides, right? So basically we have got two scenarios here. Out of HCl, HBr and HI, peroxide can influence organic peroxide, that is ROOR. Such kind of a thing can only influence HBr. It cannot influence HCl and HI. So even if you are given peroxide, organic peroxide along with HCl and HI, then the addition is only Markovnikov based. It is not anti-Markovnikov addition. But in case of HBr, if peroxide is not present, that is in absence of HBr, absence of peroxide, HBr acts like Markovnikov reagent. Otherwise, in presence of peroxide, it acts like anti-Markovnikov reagent. That's the only difference you have got, right? Fine. I still hope that there is no doubt. Please feel free to ask any doubt that you want me to answer. Right? Okay. So now how this whole thing takes place? This bromine free radical is generated with the help of peroxide. Right? Like benzoyl peroxide, it helps in generating this bromine free radical, which attacks the alkene, forming a more stable free radical. See, secondary free radical is formed here. Fine. This attacks your HBr molecule again and ultimately gives you a product which is very anti-Markovnikov in nature. Right. So one bromo is obtained. In case of Markovnikov, we had got 2 bromo. Here we have got 1 bromo thing. Right. Acha. So let's study how this whole thing is happening. Anti-Markovnikov. In brief we discussed in the last segment only. But let us try to quickly see how this whole thing is happening. So you can see that your HF, HCl and HI, they are not giving your anti-Markovnikov addition product even in presence of peroxides, right? So what they do, whether your peroxide is present or not, these 3 will always give you Markovnikov addition. Right? They will always give Markovnikov addition, nothing else. Fine, I hope this much is clear. Now let's try to understand how this mechanism is taking place, how the anti-Markovnikov effect is coming into effect with the help of each single step with the help of mechanism. So what is happening in the first step? So in the first step you can see that your homolytic bond cleavage takes place between your OO peroxide bond, right? So basically you have got this thing and this thing, so they part away homolytically. So bifurcation is taking place from here. So when you heat them or you give them ultraviolet light, so this is what generally happens, and you have got 2 alkoxide free radicals, right? So once it forms 2 alkoxide free radical formed, it is going to attack your HBr, extracting hydrogen and forming alcohol, right? So you can see that once it is formed, it is going to extract this hydrogen, form alcohol, and it will also generate bromine free radical, right? Now this bromine free radical is going to attack the propene molecule or the alkene molecule for that matter, right? So in the third step you can see that it attacks this, and this is where you get your bromine is attacked and your free radical is obtained over here. So you can see that very well. 1 electron goes with the bromine atom, the other one is moved over here. Now being secondary radical, it is relatively stable, more stable than the primary one, right? And that's why, because if bromine had come at the center, you would have got primary free radical, which is less stable with respect to secondary radical. So in the last, again, since this is formed, a new free radical is formed. This is again going to attack HBr and extract hydrogen as the last step. See, it attacks hydrogen, it is extracting this part, and what you get is this, and again this bromine free radical is formed. It will again go back to third step, fourth step, repeat, third step, fourth step, repeat. So once this is initiated by the organic peroxide, this reaction can take care of itself further by going in this very fashion. So I hope till here it is very much clear to all of you, right? Now we talk about formation of vicinal dihalides. Now in class 10th also you might have studied your unsaturation test. So basically what we do, if you take like bromine, why bromine and why not chlorine? Because chlorine is colorless, so you will not even know whether it is getting added or not. Visually there is no hint, right? So in case of bromine, which is brownish in color, you have dissolved that in CCl4, and then if you add some unsaturated say hydrocarbon to it, like alkene or alkyne, so slowly decoloration will take place. But why this decoloration is taking place? Because bromine is gradually reacting with the alkene and adding both the bromine atoms to carbon atom. If you add chlorine, the same thing is going to happen. The only difference is that you will not come to know whether the reaction has taken place or not. Visually, we will not come to know. Maybe once the reaction has taken place, we can give it certain amount of time. We can have now mixture analysis, compound analysis. Then we'll come to know, okay, whether chlorine has reacted or not. But visually, there is no way you can tell that whether chlorine has reacted or not. Hence, bromine is very good for this, because orangish color, brownish color vanished and it became transparent. So it's very much evident, okay, bromine got added over here. Now you can see that since both the carbons are, adjacent to each other, and we discussed in last class, such a dihalide is called vicinal. Had both the additions on same carbon, then it would have been your geminal. Now a way to prepare geminal is you can see it with the help of propine. We discussed in just few moments back with propene. Now if you see, you have got propine and say you add HBr. So again the same thing, Markovnikov addition. There is no hydrogen at the central part, central carbon, there is one hydrogen. So rich gets richer. So this terminal carbon is richer right now with respect to the interior carbon, and this rich carbon is going to become richer by adding one more hydrogen as a major product. I'm talking about the major product. So it will be something like this, and one bromine will come here. So when you again add HBr to it, what is going to happen? It has got now two hydrogens. So this third hydrogen will also go over here. I'm talking only about the major product. So you will get both the bromines on same carbon like this. Now this is this compound is geminal diboride. I'm not saying propane, I'm just in the similar fashion. It is a dibromide, it is also a dibromide, right? This is how it takes place, right? Okay, so I hope this part is also very much clear. Now comes the third interesting way of preparation of your haloalkanes, and that is by halogen exchange. Because we have prepared chlorine, we have prepared bromoalkane, chloroalkane, but we are yet to make exclusive fluoroalkane and your iodoalkanes. So there are two reactions, one is this Finkelstein and the other one is your Swarts reaction. Finkelstein reaction and Swarts reaction, where you can exclusively make iodoalkanes and fluoroalkanes, right? So basically what you are doing, you are initially taking chloro or bromoalkane, reacting that with the help of NaI, or you can take Ki also, right? And we do this reaction in dry acetone, right? What is dry acetone? Acetone devoid of any moisture, right? It does not have to be a dry one. I mean, it does not have to be your solid one, a powdery one. It is very much liquid in nature. So exchange took place. It's like a displacement reaction, double displacement reaction. So R gets I, Na gets X. Now the good part is, it in dry acetone, what happens? Just one second. In what happens in dry acetone, sorry, that screen went away. Yes, Lakshmi. Just 1 second, I think the connection. I'm not sure if the connection is on. Let me cross check quickly. Okay, because I cannot see myself here on the ongoing class. Let me quickly check. Okay, fine. I thought the net has dipped. Okay, anyway, so thanks for responding. Thanks Lakshmi. Thanks Shivaranjani. Um, okay, so basically what we have here is why we use dry acetone. See, sodium halide being an ionic compound is not very comfortable with dry acetone, and hence it precipitates. We know that like dissolves like, right? You must have studied that in solution chapter. So it keeps on precipitating. So when one of the products is eliminated from the net output, what happens then? As per Le Chatelier principle, your reaction keeps on moving forward. So more and more of this product is formed when you keep on removing this in the form of precipitate. So that's the main benefit of having your dry acetone as your solvent, right? Okay, now Swarts reaction, as we talked about. So because it is very difficult to prepare, fluoroalkanes, bromoalkanes, chloroalkanes, iodoalkanes. To some extent you can prepare. Now they are so reactive, so violently reactive, that you need a controlled separate method of preparation. So to prepare them, again it's kind of a displacement reaction, hence exchange we are saying, right? Again double displacement. We have got these selected fluorinating reagents, so they selectively replace bromine or chlorine and put fluorine in their place. So both bromoalkane and chloroalkane will do the trick, right? Yep, thank you. Okay, so that is how you do the halogen exchange reactions with both fluorine and iodine. Again, good for your you can say conversion reactions, step up reactions also. It is quite good. So for example, if you are given, say, you are asked to convert, say, propene to 1 fluoropropene, or say 1 iodo, sorry, not 1 iodo, 1 is here, 3 fluoropropene or 3 iodopropene, right? So now I guess you can connect the dots. How to do it? Quickly, can you think about the answer? Anyone? So convert this first, again in presence of, that is allyl addition has to be there, right? Say Br2 in presence of sunlight, or you can take NBS also, right? N-bromosuccinamide, sunlight you can have. So you replace this, bromine will come over here, and then you do the Swarts reaction like AgF, and there you go. So it's these very simple questions can be there asked in board conversions, and from there also these are the basic stepping stones from where we can slowly build up to your NEET or JEE level. So no need to worry, right? Okay, fine. Last one is your Hunsdiecker reaction. How do we go for the Hunsdiecker reaction? It's a very interesting reaction, and it is also kind of a step down reaction. Why step down reaction? You can see that initially you have 2 carbons, but you end up getting 1 carbon only. So what do? You take the silver salt of the respective carboxylic acid. So if I write the general reaction for this, it is going to be something like this: RCOOAg, right? So you can say that we have got if R has got, say, n number of carbons, one carbon, so it is n plus one carbon atom you are starting with. So you are reacting this with bromine in presence of course CCl4, CH2 will also do carbon disulfide. So what you will end up having, Ag and Br will go, carbon dioxide will move out, so you are going to have RBr. So it's a step down reaction. It is a step down reaction. So ultimately the product you are going to have is going to have one carbon less, along with of course AgBr and carbon dioxide will be formed. So since this is getting eliminated, whenever this happens, it is generally your free radical mechanism. It is always a free radical mechanism, right? So this always involves your free radical mechanism, right? One carbon less, hence it is a step down reaction, right? And your generally you'll always get that the alkyl bromides that are being formed is in this order, which indicates somehow steric hindrance is also playing its role, right? And with iodine you get something different, so you end up getting an ester. So this is how your Hunsdiecker reaction takes place, right? Please feel free to ask any question that you have got. So here we come towards the end of the session, and we are going to answer these 4 simple questions which are there in your NCERT also. The first one is a straightforward one, right? So when you have got this ROH, this is the best product, this is the best reagent you have got for chlorinating. So what is going to happen? This OH will be replaced by Cl from here. Agreed? And along with that you are going to have sulfur dioxide which will escape, and you are also going to have gaseous HCl which will also escape, right guys? So this is going to be your main product. Fine. Okay, now you have got benzene. You can see you have got benzene and you are having bromine with heat or ultraviolet light. Now you can see that again this bromine is not going to impact any hydrogens present on the benzene ring. So other than that you have got this benzylic carbon which is highly reactive position as far as free radical substitution is concerned. So this hydrogen will be removed and one bromine will be added over here. So you are going to have nitro is here, if I draw it in a vertical position here, and bromine is going to come here. As far as monobromination is concerned, if you add another bromine, it will also come on the benzylic carbon only. Right now we are talking only about monohalo products, right? Okay, third one, you can see that there are 2 OH, so by mistake we may remove both the OH, but we should not do that, because any OH on the benzene ring cannot be substituted so easily under room temperature conditions, under ordinary conditions, right? Because of resonance, partial double bond will be there, so it is very difficult to break this particular bond. However, this is on the side chain on the benzylic carbon, so it can be easily replaced. So this chlorine is definitely going to attack here and replace this. So what is going to be the output? This OH will not go, but this will go and you will get chlorine over here, right? I hope this is also very much clear to all of you. And the last one, see, nothing has been told here. That means it is a simply Markovnikov addition, hence this double bond will go, and as per the Markovnikov addition, the major product, this is a tertiary position, right? So the major product will be this CH3 here and iodine over here. This is the major product, and if you want the minor product also, so in minor products this is CH3, all right, and iodine will be coming over here. This is the minor product, right? But if there had been sunlight here, then allylic addition will take place. Remember, allylic addition, if in case of sunlight or ultraviolet light or heat. But for that, what do we need? Hi or I2 or Br2. So in this compound only, suppose if I add Br2, then it is going at the allylic position. So whether you add it here or this position is one and the same. So bromine will be here. But if you add this in presence of CCl4, then both the bromines will add up over here. So these are the things that you have to take care of, right? So with this, we come to the end of the session. So we have done all the preparations that is there for alkyl halides. So tomorrow we are going to cover preparation of aromatic halides and move on to the physical properties from there. So I hope today's session was well enjoyed, right? If nothing else. So if any doubt you come across any doubt, please feel free to ask there in the doubt segment or in tomorrow's class. I'll be more than happy to answer all of you, right? So have a good day, and it's adios from Rahul sir. Bye. Take care.